I'm going to talk about something called the HARint space, and I'll explain where HARint comes from. Last year I spoke about the HARint plane. So we were in 2 dimensions. We're hopefully moving to 3 dimensions today. I'm going to talk a bit about current practice in elevated traffic design. I'll review, for those of you who weren't here last year, we'll just talk very, very quickly about the HARint plane. I'll show how the HARint plane warns you about unacceptable designs, wasteful designs. Then we'll talk about user requirements. And our next speaker will be interested in user requirements, Len, because he's basically a client. Is that right, Len?
Yes.
Yeah, he's a client, and he's on the other side, and he's going to be looking at those user requirements. So trying to build a bridge there. I'll give you a numerical example. And then I'll talk about gravitating. What do we gravitate? And what do we mean by gravitating towards something or someone? Adding average waiting time. And then I'll compare the plane and the space. How do the plane and space compare, and how are they different? So if we look at, we have 2 general approaches. And for those of you who attended the traffic forum yesterday, there was a lot of discussion about calculation and simulation. So calculation, usually we always want to find the number of elevators, their speed and their capacity. But instead of simulating, we just actually calculate a round trip time, divide by the target interval, and you get the number of elevators. Life used to be so beautiful and so simple until simulation came along. There are 2 methods which I put forward for calculation. Analytical methods, where you have a formula, and you put numbers in a formula and a number comes out. Or numerical methods, where it's very difficult to find an equation, so you have to find a numerical method, Monte Carlo simulation or Markov chain or anything. We can use Monte Carlo simulation or equations to find the round trip time, the average waiting time, the average traveling time. So that's a quick introduction about calculation. When things get really complicated, or if we want to assess more parameters, we have to use the simulation realistically. And we can use it to assess the different group control algorithms. We can divide simulation, and I have big arguments with Richard about this, but discrete event simulation, we actually do things at certain points in time. We're not interested in what happens in between. So if I start walking towards that door, you're only interested in the point that I started walking, how long it took me, and the time I got to the door. You're not really interested how I lifted my foot and whether I looked left or right while doing that. And that makes things much simpler. Or, in some cases, we are interested in what happens in between. And we use for that time slice simulation. We pay a cost for that, but there are benefits. So that's just a quick introduction to calculation. And there are big 2 schools: calculation, simulation, and there are fans of each method. You'll find out which one I'm a fan of later on. So this piece of work, it actually closely relates to calculation. I believe there's still a lot of mileage in calculation. It does have its limitations, but I think there's a lot that it can tell us. And what I'm trying to do, or this piece of work tries to arrive at an optimum solution in a clearly defined number of steps. I'm sure a lot of people here will say, please give me a clearly defined number of steps to get at this answer. I don't want all of this book. Give me a summary, a 1-page summary of CPC Guide D, if only we could do that. And without the need for trial and error. And that's what I'm going to try to give you here. What the HARint plane builds on last year's work, it gives us 4 user requirements. And I tell my students, any design has to start with user requirements. You go to buy a machine, a mixer, or a microwave oven, you actually have user requirements in your mind. You might not think of them as user requirements, but they are user requirements. You only want to do the chicken, so you don't need something which is that big, yes? You always have user requirements in your mind. And Len has user requirements in his mind, or his boss has, and he has to follow them. So we'll talk about what the user requirements are. The HARint plane is obviously a plane. It's X and Y. And we've used graphical methods in other spheres. Evans, 1948. Where's Liz? Is Liz here? 1948. We actually use them as well somewhere much closer to home. If you look at the body mass index, each one of us is actually a point on this curve. So, I don't know here. Weight in kilograms. Each one of us has a weight in kilograms. We don't like to think about this, but eventually we have to come and look at it and see what color we come out. And then the height in centimeters. And each one of us, without telling me, you can think of yourself and see where you are on that plane. And effectively, this is a plane, isn't it? It has 2 numbers. You plug in the numbers and you end up with a point somewhere here or here or here and so on. So we use planes in our life, don't we? And it's the same here. Sorry? I can't tell you. So the HARint plane. The HARint plane, it uses one axis for quality of service, one axis for quantity of service. It's an acceptable design. It has to satisfy two simultaneously. What are the two conditions? For the quantity of service, I'm saying that this is the user requirement, and that's what our design will achieve. So we have an arrival rate of passengers in 12%, 15%, 13%, and you have to have a design which actually meets that. So that's the first requirement. And then quality of service, we have a target interval, and we have to have an actual interval which meets that as well. If we meet both of those, we've met the HARint plane requirements. These are two user requirements. In practice, obviously, we can't make them exactly equal. So as long as that is more than or equal to the arrival rate, then that's acceptable. And as long as this is less than, so this is less than or equal, that's more than equal, that's an acceptable design. If it's much more, then it's a wasteful design. And if we look here, there's the x-axis, which is the actual interval, and that's the y-axis, which is the handling capacity. On there's a horizontal line called the arrival rate. That's what we want to be above. So we want to be above that line. We want to be somewhere here. And then we have the interval, and we want to be below a certain interval. So if you overlap these two, that's where we want to be. We want a design that is actually in this area. Too high will be wasteful, because the client wants, I just want to be above this and behind this. So this is the optimum point. I can't stop there exactly, so I'll probably move a bit away from that. But as near as possible to that point will be an acceptable design. Unacceptable, unacceptable, unacceptable. That fails on quality and quantity. That passes quantity but fails quality. That passes quality but fails quantity. That meets quality and quantity. But we don't want to be too far from there, because then it's a wasteful design. So you can start to visualize now. I'm helping you visualize where you are. And as a starting point, remember I said a clear number of steps. We want to go through a clear number of steps. And the first step is to find P. That's a nice yellow background, black lettering. And it tells me what to start with P. How do you usually start with P? Well, you do a guesswork. I'm trying to help you take away the guesswork and start with a specific value. So I'm saying, depending on the two user requirements, and there's the building population, the target interval, you come up with a number of passengers. That's the number of passengers you would start with. You calculate the round trip time. And once you plot the HARint plane, you will find we can't have half a lift. You can't buy half a lift. You have to buy a whole number of lifts. So there's 1, 2, 3, fails. We have to go up to 4. 5 is wasteful, 6 is wasteful. So you immediately know by just looking at the plane whether it's acceptable or wasteful. You will end up with this point. 3.4 is not acceptable. We can't buy 0.4 of a lift. If we could, we would save a lot. But I don't know how 0.4 of a lift would look like. So we'd have to move up to 4, and we have the starting point. Other sets of lines is the constant P. So that's P, and that's the P that all of those points that lie on this line have the same number, which is P 6.4. So once we put all of those together, you will actually notice that the lines, the L lines and the P lines, are nearly perpendicular. And then you can see now that we have from the P, there's the hypothetical solution. Once we round up from 3.4 lifts to 4, we moved up to this point. And then obviously we will go back down and settle on the AR line. And that's the difference. I mentioned this last year. For those of you who use Elevate, this is the difference between up peak and enhanced up peak. You just end up on 12%. So at this point, you've achieved two things. You've achieved the quality of service because you're behind that line, or to the left of it, and you achieve the quantity of service because you're just above this line. It's optimum and it's an acceptable design. That's the HARint plane. And that's just a closer look, a zoom up. This is just an overview of the whole method. How can a design be unacceptable? 3 reasons or 4 reasons. You are either forced to have too few lifts by the architect. So the architect says you can only have 3 lifts and you need 4. We'll see where that is. That's an insufficient design. Too high, for some reason you had too many lifts. It's the wasteful design. You started with too many passengers. That's a wasteful design. Or you started with too few passengers. And the 4 of them are shown here. So if the architect says you can only have L2 lifts or L1 lifts, which is lower than what you need, what will happen? You will move down to L2 and then move back. This is a failed design because although it meets the quantity of service, it doesn't meet the quality of service. It's to the right of the line. And the same if you had to have L1 lifts. That's a good design. That's the wasteful design because you had more elevators than what you need. How can a design be have too few passengers? If you had too few passengers, you will move to this. And you don't have enough passengers to meet the design because you started with a small number of passengers. Best thing is to use the formula with the yellow background. What are the 4 users? Now we're going to start moving from the HARint plane to the HARint space. And when you move from a plane to space, you have an extra dimension. And that extra dimension is speed. So these are the 2 original user requirements. And I'm suggesting we add another 2 requirements. Now, a point of warning here. I might not have used the correct definition of traveling time and waiting time in accordance with the traffic forum. I need to correct that. But regardless of whether you agree with that or not, you can use whatever definition you want of this and this. So you might have slightly different definitions of traveling time and slightly different definitions of waiting time. But now we have 4 user requirements. And by having 4 user requirements, you will have a design that actually tells you more. And then you have a compliant design which meets all the 4 user requirements. So let's take a numerical example. This is an actual building, total population. Using 3 speeds. With the HARint space, we can use more than 1 speed. You remember the discussion we had about 20 dividing by 20 this morning? You can try to have a range around 20. So you divide maybe by 15, divide by 20, divide by 25. It gives you a range of speeds to start working from. I've just put simple values for acceleration, jerk, door opening time, and door closing time. The 4 user requirements, 12%, 30-second interval. I've used randomly these numbers, arbitrary, you can use different numbers, but I've used 60 and 10 because they fitted nicely with the example. They gave me a nice answer. And this is now the HARint space. It becomes a bit more complicated. That's why it's color-coded. There's L equals 1, 3 lines with the 3 colors, 3 speeds. L equals 2, L equals 3, L 4, 5, 6, until you get to 10. These lines, the black lines, are the P lines. These colored lines are the L lines. And you can see they actually intersect nearly at right angles. And what we can start imposing on them, we can start putting average traveling time and average waiting time on the same curve. So if we zoom in, you can see that's 4 lifts at the smallest speed, 4 lifts at the next speed, 4 lifts at the next speed. Then to move further, it's ridiculous increasing speed above that value. You're not going to get that much benefit. So what do you have to do? Increase the number of lifts. So you go 5 lifts at the lowest speed, 5 lifts at the medium speed, 5 lifts at the high speed. To go further, notice we're moving this way towards better solutions. As we increase speed and number of lifts, we move towards the optimum. Then we have to increase the number of lifts. So we go to 6 at low speed, 6 at medium speed, 6 at high speed. We haven't said anything yet about average traveling time, average waiting time. So we'll add average traveling time now. And you will see for this curve, it has, for the 3 different speeds, 3 values of traveling time. For this one, 3 values of traveling time. And for this one, 3 values of traveling time. We wanted 60. That doesn't give us, none of those give us 60 seconds for traveling time. So we have to discard that, and we have to use that. Even though that would have given us a good solution with the HARint plane. But now we have an extra user requirement. We have an extra constraint. If Stefan is here, the word constraint, we might have an extra constraint. So because we have an extra constraint, we've had to do something new. And in order to be below, well, that doesn't even give us 60, so we have to use this to get 60. Any one of those, that number of passengers will give us 60. Now we carry on this line and move until we get to the optimum solution. Waiting time, I'm going to talk about in more detail. But for now, we can also show the waiting time on this solution and the waiting time at this solution. Because we wanted 60, we had to move up this curve, go up, and then come down. We met the waiting time. we met the traveling time, and we also, obviously, we've met the interval and the handling capacity. So, why is the AR line very important? Everything seems to gravitate towards it. And the word gravitate, move towards or be attracted to a place, person, or thing. Children will gravitate towards the sweets cabinet. Participants will go to the bar usually. That's probably accurate. And in the same way, we will gravitate towards the AR line. If you imagine a fruit bowl, if you had a bowl and you put a marble in there and you move the marble around, where would it settle at the end? It'll always settle in the middle of the bowl. So in the same way, everything goes to the AR line. And that's shown here. So all the designs will eventually go back and settle on the air, because that's an input. Well, yesterday we had that with Yanni's presentation. You excite a system with an arrival rate. It's like an input. A building manager says that many people will arrive today. So the input to the system is actually the arrival rate. And the output is, so we always have an actual arrival, which is the arrival rate, which is the number of passengers arriving. So everything will eventually settle on that nice horizontal line. It will gravitate towards it. That's why it's important. And for that reason, the average waiting time will be gradated. And this is another G. I'm going to show a simple formula for the average waiting time, because I know you will say, how can I calculate the average waiting time without simulation? So one of the big challenges for this method is to have formula for calculating traveling time and waiting time. Then we're free of simulation completely. Sorry, I'm just joking, I'm just joking. If we can find simple formula for waiting time and traveling time, then we can, that's a suggested formula which I've derived, but it's outside the scope of this. I'm just going to flash it there quickly. And it's a simple, it's valid on the AR line. Gradate, rather than graduate, is actually to put gradations on a line. And that's what we're going to do, try to do here. So using that formula, we will gradate the AR line with the values of the average waiting time. So it's like an hour scale. The AR line is like a scale which has gradations of the average waiting time at the first speed, at the second speed, at the third speed, and for all speeds combined. So again, we have for 3 lifts, the 3 speeds, for 4 lifts, the 3 speeds, and each one of them has a value of average waiting time. And the average waiting time changes not linearly from 15.45 to 1.64. Not linearly, it's not a linear scale, because it has that equation in there. And then you can start seeing, in order to achieve a certain value of a waiting time, you can gradate this better in a better way, but you can see where to stop. And you can see how there's no overlap until very late on between the speeds, between the lifts, number of lifts. So you get to the top speed of the number of lifts, and then to move next, you have to increase the number of lifts and then drop down again to the lowest speed. So 4 lifts at 4 meters per second is worse than 5 lifts at 1.6 meter per second. Lifts are much stronger. They have a much, obviously they cost more if you increase 1 lift. So nearing the end, I was always told never to apologize for a short presentation. User requirements. It was actually for a short meeting. So let's compare the plane and the space. The plane had 2 requirements, 2 user requirements. The space has 4. The optimal outcomes. We get the number of elevators for the plane, but for the space we get the number of elevators and the suggested rated speed. By product, we actually get the passenger numbers and hence the car capacity. And possible triggers, which I haven't investigated here, but basically people are talking about 16 lifts in a zone. The rationale is actually the traveling time. You can start putting a set, and if you can't achieve that traveling time, no matter how much you increase the speed, you've got to zone, you've got to start zoning. So unfortunately, all good things have to come to an end. And this presentation is no exception. Ladies and gentlemen, thank you very much for being a great audience.